Hello friends, welcome to our new session in Control Engineering for BE 7th semester Mechanical Engineering. In this session, we are going to start with the third module. Under third module, we are going to study today steady state operations, where we are going to know about steady state analysis for a general block diagram for a control system. Next, steady state characteristics and equilibrium in a system. So already we know what is steady state operation and why steady state is required in a case of a control system. Under this steady state operation, we are going to know more about the method to determine the steady state error. Let's see steady state analysis for a general block diagram for a typical control system. Here, derivation of obtaining a steady state error for a given system is going to be explained now. So, the steady state response is important to judge the accuracy of the system. The difference between steady state response and the desired reference gives the steady state error. And this steady state error is denoted by letter ESS. Let's consider a simple closed loop system as shown in the figure. Here in this closed loop system, we are having a forward block, here in the closed loop system we are having a forward block, a feedback block and a summation point and a takeoff point. So in this typical closed loop system we are having the input R of S, error E of S and the output controlled variable C of S with a feedback signal B of S. From the figure, we have error signal E of S is equal to R of S minus B of S. Let's, for this case, consider the feedback signal is negative. So we have E of S equal to R of S minus B of S. So this one we'll quote it as equation 1. Similarly, B of S output from the feedback block is equal to H of S into C of S, the output taken from the controlled signal C of S. So this is equation number 2. Therefore, E of S will be equal to R of S minus H of S into C of S. So this will be our equation number 3. Here we need to find out what is C of S equal to. From the given block C of S, the output variable is equal to product of G of S and H of S. So we get C of S is equal to G of S into E of S. So wherever we have in equation 3 C of S, we are going to substitute it by G of S into here E of S. So what we get? We get E of S equal to R of S minus G of S into E of S into H of S. Here we are rearranging this equation. We get E of S equal to means this minus g of s into e of s into h of s is taken other side. We get e of s plus g of s into e of s into h of s equal to r of s. This is equation number 4. So we have here e of s, here e of s. Taking e of s common, we get e of s equal to r of s whole divided by 1 plus g of s into h of s. So this is equation number 5. Here when we are having initially a negative feedback, we will be getting here in the denominator plus signal. If we are having a positive feedback, then here we are going to get a negative signal here or a negative sign. Hence error is equal to r of s whole divided by 1 plus or minus g of s into h of s. This error signal is in a s domain. So we have to convert this one into a time domain function. That is what this Laplace domain or expression is in a s domain. We want to calculate the error value in a time domain. The need of calculating the error in a time domain is the response curves or response outputs will be on a time function. Hence we have to convert the s domain into a time function to predict the response of the given system. In the time domain, we have e, a function of t, is equal to inverse Laplace transform of e of s, or Laplace transform of e of t was capital E of s. Hence small et is equal to inverse Laplace transform of capital Es. So this one we write it as equation number 6. And this expression of error is valid for all time. Now for a steady state error, that is ESS, it is defined as ESS is equal to limit as t tends to infinity for a function et. From the final value theorem in Laplace transform. In a Laplace transform, we have the final value theorem which tells that limit as t tends to infinity et is equal to limit s tends to 0 s into e of s. Hence here limit t tends to infinity into e of t. Hence steady state error can be written as in the similar manner. Wherever we have e of s, we are going to substitute this one. So here we get ESS, that is steady state error, equal to limit s tends to 0 s into, here we had e of s, we are going to substitute it from equation 5, that is r divided by 1 plus g of s into h of s. Hence steady state error equal to limit s tends to 0 s into r of s 1 plus g of s into h of s. This is a very important derivation, many are times asked in the examination. Based on this itself only, we are going to solve some of the numericals. So do remember this equation. Next we are going to talk about the characteristics pertaining to this steady state error for different inputs. Let's discuss on steady state error and its characteristics. Here in the steady state error and standard test signals. So what type of output you are going to get when the steady state errors for different types of inputs it is getting subjected, or in terms of the relationship between steady state error and standard test signals we are going to discuss. And here we will be coming to know the characteristic of a steady state curve for the given type of input. Let's go one by one. Here we are going to first study about the steady state error for a step input. So as we know about what is a step input, a step input is having a magnitude of A or R applied for all values of t greater than 0. Hence we can write it mathematically as the response term, that is R function of t or Rt is equal to A into u of t for all values of t greater than 0, and it will be equal to 0 for t lesser than 0. Taking Laplace transform for this above equation, we get Laplace transform of R of t is equal to R of s, and Laplace transform of A is equal to A divided by s, where Rt is equal to ut. So we know that steady state error ESS t is equal to limit as s tends to 0 in the numerator s into R of s or divided by 1 plus g of s into h of s. Here wherever we are having R of s, that is this term R of s, we are going to replace it by this equation, that is R of s is equal to A divided by s. Hence we get ESS t equal to limit as s tends to 0 s into A by s in the numerator or divided by 1 plus g of s into h of s. Here we will be cancelling s and s in the numerator. We are left out with the term A. Hence we get as below ESS for a function of t equal to limit s tends to 0 A divided by 1 plus g of s into h of s. Taking the limit into this variables, here we get ESS function of t equal to A divided by 1 plus limit s tends to 0 g of s into h of s. Here limit s tends to 0 into g of s into h of s is defined as a constant, that is a positional constant. So hence this is replaced by a positional constant as Kp. So what we get here is, for a step input, ESS is equal to A divided by, that is magnitude or amplitude A divided by 1 plus Kp. As I have told, the positional constant Kp of a given system is defined as Kp is equal to limit s tends to 0 g of s into h of s for a given open loop system. When a step input of a magnitude A is given, in a response it gives a steady state error ESS equal to A divided by 1 plus Kp, which is a steady state error. So when we are going to plot the curve or the steady state error output response for a given input, we get the desired output in this manner. Suppose we have given a step input with a magnitude A for all values of t greater than 0. This is the ideal output which we need to have. But because of the oscillations or a response or because of the inertia into the system. So what we get? We get some output oscillations in the beginning, and later after some duration of time it is going to get settled down, and there will be a offset between the desired output and the actual output, which will be remaining throughout the process, and this offset will be called as steady state error. That is found out by this term, that is ESS is equal to A divided by 1 plus Kp. So this is a typical characteristic for a steady state error of a step input. Next, steady state error for a ramp input. A ramp input of a slope A is applied to the given input. Hence, it is given mathematically as small r t equal to A into t for all values of t greater than 0, and it will be equal to 0 when t lesser than 0. Applying Laplace transform on this above equation, what we get? R of s equal to Laplace transform of et. So a is a constant, so it will be a divided by s square. Hence, we already know that steady state error ESS for a function of t is equal to limit as s tends to 0 s into R of s whole divided by 1 plus g of s into h of s. Here we are going to substitute R of s by a divided by s square. So later we can see here steady state error for the above system will be coming as ESS for a function of t is equal to limit as s tends to 0 s into a divided by s square by 1 plus g of s into h of s. Here s and this s power will be getting cancelled, remains with in the numerator a divided by s. So next, when we are going to rewrite it, we get ESS for a function of t equal to limit s tends to 0 in the numerator a whole divided by s plus s into g of s into h of s. So this s is coming here. Then applying limit in a side these equation, we get ESS equal to a divided by 0 plus limit as s tends to 0 s into g of s into h of s. So limit in the denominator, limit s tends to 0 s into g of s into h of s is given by or replaced by a velocity constant, that is kV. So we get ESS for a function of t for a given ramp input equal to a divided by kV. Hence, the velocity error constant kV of a system is defined as kV is equal to limit s tends to 0 s into g of s into h of s. So the characteristics for this type of output here is, here we can see a ramp type of actually output, desired output, sorry, ramp type of desired output, and we are having a oscillatory type of actual output for during the transient phase, and then we get a offset from the desired output, which is going to be measured as error, that is ESS is equal to a divided by kV. This is the characteristic for a ramp type of input. Next, steady state error for a parabolic type of input. A parabolic input of a slope coefficient of a by 2 is applied, that is RT is equal to AT square divided by 2 for all the values of t greater than 0, and it will be equal to 0 for t lesser than 0. Applying Laplace transform on the above equation, that is Laplace transform of RT is equal to R of S, and Laplace transform of a t square divided by 2 will be equal to a divided by s cube. And we already know that steady state error ESS for a function of t is equal to limit as s tends to 0 s into R of S divided by 1 plus g of s into h of s. Replacing R of S by a divided by s cube, we get here ESS for a function of t is equal to limit as s tends to 0 s in the numerator s into a divided by s cube whole divided by 1 plus g of s into h of s. So here this s gets cancelled with this s cube remains with s square. So what we get, a divided by s square. Then we are going to bring this s square in the denominator term. So what we get, a divided by s square plus s square into g of s into h of s. Applying limit for the s domain terms, what we get, ESS for a function of t equal to a divided by 0 plus limit as s tends to 0 s square into g of s into h of s. So the denominator term limit as s tends to 0 s square g of s h of s is equal to a acceleration constant, that is Ka. Hence we get ESS for a function of t equal to a divided by Ka, where Ka is the acceleration constant for a steady state error for a parabolic input. So the acceleration constant Ka for a system is defined as K is equal to limit s tends to 0 s square into g of s into h of s. Here we can see a typical parabolic curve for this is the actual curve, the desired curve, and here we can see the oscillatory curve which is following the desired curve path, and we can see there is a offset between the actual and the desired curve. That offset is called as a steady state error, that is given for a parabolic type of input, ESS equal to a divided by K. Let's summarize for the steady state error for a different input signal. So here we are having for first the step input, the steady state error is given as ESS for a function of t is equal to a divided by 1 plus Kp, where Kp is a proportional error constant, and the expression for that one is Kp is equal to limit s tends to 0 and product of the open loop transfer function g of s into h of s. Similarly, for a ramp input, ESS for a function of t is equal to a divided by kv, where kv is velocity error constant, that is given as kv into limit s tends to 0 s into g of s into h of s. And for a parabolic type of input, ESS for a function of t equal to a divided by Ka, acceleration error constant Ka is given as Ka equal to limit s tends to 0 s square g of s into h of s. So based on this steady state error and the expressions for constants, we can determine the values of these constants, and we can able to find out the steady state error occurring for the given type of inputs. So using these expressions or formulas, we are going to do the calculations. Let's understand or go through a relationship between steady state error and a type of system. So this will help to solve the numericals and to understand what type of system is the given open loop system or a closed loop system. A type of a system means the number of poles G of s, H of s at s is equal to 0. Now regarding these poles and zeros, we'll be talking it later, but at right now, if we want to know what are these poles means, these are the roots of characteristics of this open loop system G of s, H of s, means roots at the denominator of this equation. Let's consider a general form. So the general form of G of s of H of s is equal to, in the numerator, k bracket 1 plus t1 s bracket 1 plus t2 of s, similarly so on until 1 plus tm of s. In the denominator, we are having s to the power n bracket 1 plus ta of s bracket 1 plus tb of s, so on till 1 plus tn of s. So the term should be in this form: 1 plus t1 of s, 1 plus t2 of s, so on, or tau 1 of s or tau 2 of s. So this will be. Here we can see n poles at s is equal to 0. Here s to the power n at s is equal to 0, hence the type of a system is called as n. If here we are having s to the power equal to 1, then n or type of a system will be type 1. If s to the power 1 is there, means here it will be type 1 system. Type 1 system. If it is having s to the power equal to 2, then it is type 2 type of a system. So on. So the general form of this open loop system G of s is k bracket 1 plus t1 of s bracket 1 plus t2 of s, so on in the numerator, by s to the power n bracket 1 plus ta of s, 1 plus tb of s, so on. So using this generalized form, we will be able to determine the type of system. Thank you.